Okay, what I'd also like to illustrate is that there's another method that we could have used on that same problem. Okay, when we have an x on the bottom, or any kind of fraction that we can split up into two separate parts, when there's a binomial on top or a trinomial and a monomial on the bottom. Okay, we can take each of those and put them over the denominator. In other words, unadd those, if you will. Okay, and if we simplify that, that should have been x plus 3 over x. Okay. Now, if we wanted to find the derivative now that it's a plus sign, we can do these individually. Okay, and if we do this one, obviously this one's the easiest one. It's just x, so the derivative is 1. Okay, but what about 3 over x? Okay, we have two choices here. We could use the quotient rule just for this part. We'd have easier stuff to work with if we did that. Okay, we could do bottom times the derivative of the top, top times the derivative of the bottom, divided by the bottom squared, and get an answer. However, there's a little bit better way. Okay, we know that if x is on the bottom, that I could rewrite that as x to the negative 1 next to 3. True? Okay, and here's the good news. The power rule that we learned earlier, okay, that works for negative powers also. Okay, so I would make a power function out of this instead, and that way I don't have to bother with the quotient rule. Okay, so if you made a power function out of it, 3x to the negative 1, okay, then you could write that as 1, of course, the derivative. Okay, and then if I go negative 1 times 3, that's going to be negative 3 in front. And then I went x to the negative 2. And how did I get negative 2 here? Because what does the power rule state? We're going to take the power and go minus 1. Okay, so I went 1 down from that, and I got negative 2 as my power. Got to be careful here because some people are going to put 0 for that, but 0 would be going what? 0 would be going up. Got to go power 1 down. So that would make it negative 2. And then if I rewrite, then my answer without negative powers is 1 minus 3 over x squared. And we might ask, well, that doesn't look like what I got in the last problem, does it? Okay, not exactly, but if we were to get a common denominator, we'd have x squared minus 3 on top, x squared on the bottom. And isn't that the version that we had using the quotient rule? Which of those is right? Both. And they're both right. Okay. All right, and then I want to look at one more thing. Remember earlier we used the limit definition to find the derivative of y equals radical x, right? Okay. And that was not terrible to do, but if I were to write this as a power function, knowing that radicals can be written as powers, okay, does the power rule work for rational exponents? Yes, more good news. Okay, so if you have a rational exponent, okay, a fraction exponent, okay, you can still use the power rule the same way we did the others. And so when I find dy dx here, I'm going to go 1/2 in front of x, lower the power down 1, and what's 1/2 minus 1? Negative 1/2. And then again, I want to write this without the negative power, so I still have 1/2. That's going to go down on the bottom, and it's going to become radical because it's still on the bottom. It would be x to the positive 1/2. Okay, and so my final answer is 1 over 2 radical x. And if you remember, that's exactly what we got when we did the limit definition earlier. We got 1 over 2 radical a. Okay. All right. Questions so far? Okay. Garrett?
How come like last year, Mr. Shaw told us like not to have a radical on the bottom?
Well, ultimately, one of the things in calculus that one of the reasons we're gonna find derivatives is so we can use it to find the slope at a point for some function for some reason generally. Okay. So if all I want to do is put an x in here, okay, is it really necessary to get the radical off the bottom here? If all I want to do is just plug in a number and find an answer? No. So usually in calculus, we kind of start to abandon that rule. Okay. We do it in pre-calc and algebra 2 just because it's more proper to give an answer without a radical on the bottom. But in calculus, when it serves the purpose of just finding a numerical answer at some point, okay, really it would make it more complicated if I did that, wouldn't it? Because now I'd have a radical x on the bottom, top, and I'd have an x on the bottom. I'd have to plug in x twice. So really, would it make sense in terms of efficiency to do that? No. So that's why we don't. That's a great question, though. Okay. All right. Let's see. What I want to look at next is two more things real quick to finish up. Actually, oops, I got a little bit more than that. But one of the other things that we do with derivatives too is if we have an equation like 5x to the 5th, okay, we can of course find the derivative y prime, which is 25x to the 4th using our power rule. Okay, and then I did the derivative again here and I called it y double prime. Okay, y double prime represents the second derivative. Okay. And ultimately, if we were to keep taking derivatives of that new function that I create, okay, we could get a third derivative, a fourth derivative, fifth derivative, and so on. Okay, one thing with polynomials too, though, is at some point this is going to become what number? It's going to become 0, isn't it? Okay, because if I did the third derivative, which I don't have on here, it'd be 300x squared. Then I'd have 600x. Then I'd have 600, and then if I had 600, it would become what? It would become 0, wouldn't it? So eventually, in a polynomial, the derivative, however many you take, is going to become 0. In fact, I said that the sixth derivative is going to be that. It's going to be 1 more than the power, isn't it? Okay, we'd be down to 0 every time. Okay. Now, again, there's a purpose for first derivatives in terms of applications that we're going to see, and there's also purposes with the second derivative. I'm going to illustrate one right now. Okay, one of the things that we've been doing a lot was using this distance formula to calculate instantaneous velocity. True? Okay, we know that finding the derivative of this gives us velocity. Okay, and in the past we've used the limit definition to figure that out, but now, okay, we know that d prime, okay, the derivative of that distance equation is the velocity equation. Okay, this gives us our velocity at any time. So when we did the problem on the first quiz where we had to find the derivative or the instantaneous velocity at a particular time, okay, now that we know this, we could have just found the derivative like that and plugged in 2 or 3 or whatever the case may be. True? And that would have given us the instantaneous velocity. Okay, now I want you to look at what happens if we do the second derivative of that. Okay, and I want you to, before I tell you the answer to it, okay, keep in mind that when I did the derivative of distance, keeping in mind would be something like feet divided by seconds would be the derivative, right? Okay, if I had a feet per second graph versus seconds, okay, and I found the slope, that would mean this divided by this. If I did that, it would be feet per second squared. Okay, and anybody know what is a measure of feet per second squared? Okay. Keep in mind it's a rate of change of velocity. Okay, what do we call it when velocity changes? Okay, if I get in my car and I hit the gas, what am I doing? I'm accelerating. And that's exactly what we get when we take the second derivative of the distance, which is also the derivative of the velocity. Okay, we get a unit like feet per second squared, which is an acceleration. Okay, and if you notice here, and I mentioned this at the beginning, but I didn't go into it very deeply. Okay, the acceleration in this problem is 32 feet per second squared. Isn't that the acceleration due to gravity near the Earth's surface here? Okay, so is it a surprise that 16 was the number that was in front of this when we did it before? Okay, and remember the number for meters per second was 4.9. Okay, if we did 4.9's derivative, 4.9 t squared, it would be 9.8 t squared. And if we did the derivative of that, it'd be 9.8 meters per second squared. And what do we know about the acceleration due to gravity near the Earth for meters per second squared? It's 9.8, isn't it? So these aren't just magic numbers that we picked. It's because of the acceleration constant that we have here on Earth. And if we were on a different planet besides Earth, okay, those numbers might be completely different. True? Okay. All right, that's all I have for today. Okay.